Hey everyone, it's Jim
and Charles
from Mellow Amps. And in today's MTA episode number 16, we're going to talk about what in the heck is an R2R DAC. Now the alternative title was, why does digital audio mostly still suck?
We'll try not to make too many of you angry with this one.
Yeah. Now, before we get into today's episode, I'd like to welcome everyone who is new to the MTA channel. When we first started this channel, we were focused on producing content mostly about our kits. And, we're both audiophiles, and we're interested in everything to do with high quality audio. And I thought, let's expand the channel a little bit to include those investigations and prototypes and other technologies that are behind the audio that we love so much.
Because as we know, everything matters in a system, and it's kind of hard to talk about just one piece of it and ignore the rest of it.
And that brings us to today's episode. For a couple of years, we've been doing DAC development with the hopes of eventually introducing a DAC kit. Now, you might think DAC development has peaked and nothing new can be developed. And I think that's mostly true. Today's DACs can convert a very high bit rate. Bit rate is just the sum total of the bit depth. So let's say CD quality, so 16 bits. So that would be 16 bits times the sampling rate. And in the case of a CD, it's 44,100 times a second. Multiply those two numbers and you get your bit rate. Okay, so today's DACs can take an incredibly large bit rate and decode it easily. They can handle multi-channels out the yin-yang, and they can do that for almost nothing. They're so cheap they're almost free.
Cheap as chips, as some other YouTubers like to say.
I think some of the more expensive DACs get as high as $10, but they're really not expensive. Now, if those DACs could produce really great sound, a very believable soundstage, so width, depth, height, and you could listen for hours without listener fatigue, then I would say absolutely yes, the technology has been fully developed. But decidedly the answer is no, and not, in my opinion, absolutely not. Yeah, they do the decoding part right, but to me as an audiophile, there's a lot lacking in modern DACs. So what I find really interesting is that very early digital recordings made in the 1970s till about 1982, they can sound amazing. And these were recorded initially on computer tape and mastered on analog mixing desks because
the digital ones just didn't exist yet.
Yeah, I think the very first digital desks came into popular usage around 1985. And because there were no CDs, they hadn't been invented yet in the 1970s, the development work was underway, but they weren't released until 1982. Those early digital recordings were actually pressed on vinyl, and those were hyped as digital records.
Even though a lot of the work was still being done in the analog domain.
So what changed in those early digital days in the 1970s to today in the 2020s? Well, a number of things. First, many of those recordings were made before oversampling. Many of those early digital recordings were made before oversampling had been invented. And many of them were made using ladder DAC networks or early, relatively simple analog to digital converters. otherwise known as ADC chips. And we're going to talk more about that in a minute in the lab. And I think that one word, simple, says it all. In my experience, no, I didn't say my opinion. I said my experience. I should really say in our experience. The more you complicate the audio technology you're utilizing, the more the magic seems to evaporate. Okay, so up here we've got a prop, and we're actually going to open this thing up. This is
an very expensive and heavy prop.
it is a surprisingly heavy DAC, and that's because Denafrips put some money into the casework, and of course you have to pay for that. In our kit business, because we're targeting audiophiles who are on a budget, who want the best sound possible, but they just don't have huge whacks of cash. And that's the vast majority of us. I mean, years ago, I took the handle of the budget audiophile, and actually started my YouTube chops as a budget audiophile. And even though today I can afford more expensive gear, I still, I'm very hesitant about investing serious amounts of money in so-called high-end audio, because I think the diminishing returns show up really quickly. Anyways, this is the Denafrips Pontus 15th, and even though we're doing DAC development ourselves, we really needed to have a reference R2R DAC to give us a sense for how good our development work was. And this is a well-respected, well-reviewed company, and the latest version of, I would say, the beginning of their high-end line. And when we open it up, we'll take a look, and we're not going to do a complete, show and tell and crack this thing open completely, but we'll take a look at the ladder network if we can figure out how to get into it. And
talk a little bit about how R2R DACs work and how DACs work in general over in the lab.
Yeah. Okay, well, let's head over to the lab. Okay, so we're back in my lab, and the signal that we play through our DAC has to get encoded at some point. And in the studio, the captures are all done now off the analog feeds. So it's off the microphones, off the guitars, off the vocals, are all captured immediately and digitized. But how does that actually work?
Okay, so we have here a very simple representation of a sine wave. Now, of course, real music is going to have a mixture of all sorts of frequencies in it. It's not going to look like this unless you're playing a pure sine wave.
And of course, the amplitude is going to change constantly.
Mm-hmm. Now, if we zoom in really close in on this, what you can see is I've drawn in a whole bunch of little dots here, and this is to represent the samples. What is a sample? Well, whenever you see something like 44,100, that is telling you how many times our ADC, or analog to digital converter, is taking a snapshot of where the signal currently is. So you can imagine it like it's taking here, 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 and it's doing that 44,100 times a second.
Yeah, and you'll be familiar with this because Redbook CD sample rates are 44.1 kilohertz, which is 44,100 times a second.
Now, of course, there's other sample rates, and they can get really far up there. And as you get up there, you end up with more samples taken in this space. But this is how you convert something that is analog, that is one signal that's changing constantly, into a bunch of digital data.
So this distance that you've drawn in here, this is a period of time, isn't it?
Yeah.
And how much time were you talking about?
Oh, this is probably, a tiny fraction of a second right here.
Okay.
So how do you represent one of these points here? And this is where we're getting into the discussion on what a bit is. So let's clear this off and take a look at a circuit.
Oh, you've been busy drawing. Okay. Well, this is a very simplified circuit diagram of an R2R DAC. And we're going to try to explain it to you in very simple terms. And hopefully, when Charles is done with the last diagram, you'll have a little better idea how these things work. Now, first of all, this is the simplest DAC technology that exists. And nothing more simple than two resistors in a network that is series and in parallel is possible to decode a digital signal and bring it over to analog. So we start with the digital signal, don't we, Charles?
Yep. And the digital signal's just a whole bunch of zeros and ones.
Yeah, and they're going to be organized. And we're not going to get into the details of how they're getting organized. It's boring. And in fact, this is boring. But each one of these pairs of resistors basically form a decoding network that can handle 1 bit of depth.
Yeah.
And keep that in mind, because we're going to look at 1 bit of depth and then bit. So this is bit 0. This is bit 1. So we're now 2 bits of depth. This is bit 2, so we're now 3 bits of depth. This is bit 3, so we have 4 bits of depth.
I know it's a little confusing, just like with computers and programming, you always start with 0 instead of 1.
Now, to put this in perspective, Redbook CDs have 16 bits of depth, so we'd actually have 4 times this network, and it would just keep on going the way it is. So we can see that the digital signal comes in here, and how it gets in is really fascinating. And we'll do a future episode to talk about that. And on the output side, we've got a low analog voltage coming out off of this signal. And you might wonder, all of these bits, they must have equal weight in the signal.
But no, because one of them is a lot closer and lower resistance towards the output, and as you get further along, that resistance increases.
So we have something called the MSB, or most significant bit, and that means that the last bit in the chain would be called the LSB, the least significant bit. What about these resistor values? What's this R2R title? And ladder DAC, well, ladder DAC, you can pretty much see why it's called a ladder DAC. But what about R2R? Well, R2R simply refers to the resistors in the network. So there's an R value and 2 times that R value, so 2R. And people will tell you that these values don't matter, and technically they don't. But they do, because the value of 2R establishes the vast majority of the output impedance of the DAC. So yeah, the values actually do matter. So let's give you an example. So R could be 1K 0 ohms. That's 1,000 ohms. That means that the 2R has to be 2,000 ohms, yeah? And that's how you get the title R2R. Okay, now this is not that easy to understand because there's no pictorial indicator as to really what these signals are, right?
And what's happening as you're putting a signal through here. So just a quick thing before you put that away here. These zeros and ones, you can think of them like a switch. You can think of it as an on or off. So if this is on, then we have a signal coming through here. If this is off, we don't. So this is going to be really important for this next section here. Here we have another representation of a 4-bit DAC, starting at 0, going up to 3 here. And each one of these is an example of a sample that's being taken and how it's being constructed by these bits. So over on the side here, we have number 3, which is our most significant bit, and number 0 is our least significant bit. So what do we mean whenever we say most significant bit? Well, it's most significant because it is the largest portion of the signal that's possible that can be represented by a single bit being turned on or off, which is approximately half of the signal. So 3, with this color code, is equal to half of the signal being filled up at one time. So if you turn on just this bit, this is what you get. And if you go further down, every bit divides that in half. So this is how you would represent any point along an analog signal chain by stacking these bits in the correct order on top of each other to produce whatever amplitude you'd like.
So in that one snapshot, let's just say that that's one of the 44,100 samples.
Mm-hmm.
You're actually adding up the potential, well, not the potential, the actual output of each one of the bits?
Exactly.
They make a sum total?
Yes. So they all sum together. And you can do that by varying the bits that are getting turned on to match your signal. And this works both ways. For the digital to analog and the analog to digital, it's still going to be doing it the same way if you're using an R2R network for it. So you can see here we've plotted a point. This is with bit 2 turned on. Now bit 2 plus bit 1, we're a little bit higher. Bit 3 plus bit 0, we're a bit higher still. And then bit 3 plus bit 1, we're a bit higher still. And so it's doing this with more bits in most cases and way faster, thousands upon thousands of times per second.
Yeah, so as the bit depth increases, the resolution increases.
Yes, in theory, as long as your resistors and your ladder network are accurate. So you can imagine if your most significant bit is off a bit, say it's off by 10%. Well, that 10% is more than your later bits would be because you keep having to divide it in half as you go along. And this is where you start getting into trouble with accuracy issues and why doing an R2R DAC is really challenging.
Yeah, and why our research is actually taking us down into the technical side of actually measuring, accurately measuring resistances to a very high degree.
Mm-hmm. This is probably the longest amount of development we've put into anything, and it's still we consider to be early stages.
Yeah, but it's interesting and it's fun. So hopefully that helps understand a little bit. But I think actually looking at a ladder DAC on a circuit board might give you a better idea as to actually what it looks like.
Yeah, let's go see if we can get it popped open for you.
Okay. Okay, well, without too much fuss, though a little bit of head scratching, we got in. And if you look at this, you might think, actually, let me bring the camera down just a little bit here so you can see the whole thing. And tighten it down. There we go. So here's your resistor array or ladder network. And you might think, now, this is a 2-channel DAC, and there are 4 arrays of resistors. These are all just really tiny surface mount resistors. And the reason why there's 4 is because this is a true balanced ladder DAC. And what that means is we actually have a positive and negative, or an inverted and non-inverted side to each channel. So I don't know which channel is which, and the labels are so small I can't see them.
Yeah, this is our first time getting into this.
So let's just presume that this is the left channel here. So this could be the non-inverted, and this would be the inverted side. And this is the right channel, so that would be possibly the non-inverted, and that would be the inverted side. And yeah, I mean, look at the technology. It's just phenomenal. Over here, I'm pretty sure that this is the dedicated DSD side of the board. And yeah, so you can get an idea on how the actual build will look. Now, if we ever get around to building a prototype R2R DAC, we're going to be using resistors, but we'll be actually using
discrete through holes, not surface mounts.
Yeah.
So it's going to look a lot bigger than this per channel.
They're still pretty small, those little 1/4 watt resistors. And maybe we'll even use a smaller resistor than that if we can find them. We managed to find very high tolerance, or a very tight tolerance would be a better way of looking at it, 1/4 watts. That they're expensive, but they're reasonable enough. But they're still at, what are they at, 0.01% tolerance?
I think so, yeah.
At that at that tolerance, we still need to actually bring them even further down to, I think, 0.002%.
And that's what we're working on now. But yeah.
But we'll do a discussion in a future MTA video in which we actually look at measuring low resistance, and we'll probably put everybody to sleep too. But more importantly, why the resistances have to be that tight, and we'll show you mathematically why. It's really quite fascinating, but just take it for granted right now that without a very tight tolerance to the resistor network, you will never reach. I think this DAC is supposed to get to 26 bits, which is phenomenal.
And every time you add a bit to it, you have to double the accuracy of the resistor in the network.
Yeah, so I'm going to give them the benefit of the doubt that they actually reached 26 bits of resolution, but
a lot of R2R DACs don't.
Yeah, a lot of R2R DACs, especially inexpensive ones, don't come anywhere close to meeting their specifications. And you can, if you check the specifications and they're not very clear about the tolerance of the resistors in the network, or they're clearly trying to fudge something, most likely they're not reaching the bit depth that they're actually talking about. So for example, if you had an R2R DAC that claimed 16 bits of depth, you may only be actually getting 12 bits of depth.
Or if it was 24, you might only be getting 16.
Yeah. So now 16 bits of depth is fabulous. So it doesn't necessarily mean that the DAC won't sound good. It just means that it hasn't met its specifications. So anyways, hopefully you enjoyed this episode, and there'll be more like it to come. This is Jim.
And Charles.
Signing off. Cheers, everyone.